Welcome back to ECE 501B. In the countdown to all of the due dates, there's 3 different things that you're responsible for. Homework number 8 is due on Wednesday. Project deliverables 2 and 3 are due on Wednesday, and the teacher course evaluations are Wednesday. Teacher course evaluations are anonymous. I don't see those until after grades have been submitted, so you can assume, or you can be assured, that it will not impact your grade, the teacher course evaluations, and it's useful information for me to understand your perspective on what works, what doesn't work. It gives me feedback on how to adjust the class for future semesters. But leading up to those due dates on Wednesday, I blocked down a couple of hours of time tomorrow morning if you have last-minute questions concerning those particular assignments, homework or project. I'm assuming you won't need to come to me and ask about teacher course evaluations, which is due on Wednesday, but from 10 to noon tomorrow you can come see me in the normal place. The final exam is actually occurring a week from tomorrow, and it will start a couple of hours later than this class normally starts. It's on a Tuesday, not a Monday or a Wednesday, so just make note that you're aware of when the final is. It's in this room, and I think I've posted some material on D2L about the final, but you probably won't see a practice final on the preparation material. So assume that the format is similar to the previous midterm exams, but the final exam will be comprehensive. The material is by nature comprehensive, so it makes sense to have all of the material from the beginning of the course up until now. And what you will be held responsible for, and we'll talk a little bit more about this next time, but the final exam will be covering material up to and including homework number 8. That said, now lock the doors. This material today won't be on the final. Okay, so you can kind of relax maybe. Now we're in the second book today. Our goal is to talk about a subset of functional analysis, which is the book Signal Theory by Franks, and that's available to you on the D2L or the course website in the course resources section of that material. Today we will try to go through a motivational example of how can we think about infinite dimensional vector spaces in terms of how we've looked at finite dimensional vector spaces. And we'll do that by starting with the convolution operator or the convolution expression. I'm assuming you're familiar with that, and we'll use that to illustrate how we can now have eigenfunctions or signals and pass those through an operator and end up with eigenvalues through or via the convolution operator. Then we'll get into chapter 1, which is dealing with signal sets via examples. Signal sets, now think of those like you would think of vectors in the finite dimensional case. There's many different ways of representing these finite dimensional concepts with vectors. Now we're trying to find other ways of thinking about signals rather than just drawing these signals as a function of time. Can we represent them as sets? Oh, that signal is a point in this set. There's another point or a signal in this set, and can we now cluster those or group those together by means of partitioning or equivalence? So here's the second book of the semester. So now we've covered half of the semester. The second half will be in the last week in 2 lectures. So this will be a fire hose. No, we're not going to go that fast. I want to just sort of develop the connection of our finite dimensional understanding with the infinite dimensional theory that's discussed in Frank's with the book called Signal Theory. Here's how he has laid out his book. The first 5 chapters are really the foundational material, and then after that, the last 5 are applications. How do you apply this theory relative to infinite dimensional vector spaces? And that might be useful to you after this semester or in subsequent work or research. When you think of a signal, it typically, you can think of it as carrying information, especially if it's a communication signal. Now you have this communication signal that obviously is carrying information. If you have a signal in a control system, it's a particular kind of signal, and how does it get modified or changed as it goes through this closed loop system environment? And there's different ways of classifying signals. A signal could be an energy signal. By that I mean it has a bounded energy. It might be a power signal, meaning if you now have a sinusoid and it theoretically started at minus infinity and goes to plus infinity, there's no way we can talk about that signal's energy. It's unbounded. But we could talk about its power. So we could then classify signals as energy signals, power signals, band limited, time limited. Maybe these signals are only non-zero over a certain interval of time. Those are different ways of classifying signals and how we might represent them. And what we will do, or what this book does, Signal Theory does, is it takes a signal space viewpoint. Similar to how we've talked about or dealt with vectors or the finite dimensional material up to this point, you can think of vectors many different ways. You could think of a 3-vector in this room. If that corner is the origin, now you could think of a vector as the vector or originating in the corner and going to a particular spot. Or you could just think of that vector as that point. Now you have all of these points in this room that represent a vector. Those are now how maybe we can classify signals. Now if we have this set of signals, maybe these are sinusoids. Now this sinusoid is that point in this set of signals. And once we have these signal sets, can we now start performing operations on those? Maybe we now are working with sinusoids. Are there particular operations that map back into that sinusoidal set of signals? A linear system does just that, doesn't it? If you shake a linear system, excite a system, what happens after the transients have disappeared? If you hit this system with the sinusoid, what's going to come out of that linear system? A sinusoid of the same frequency. Since it's a linear system, it maybe has now just changed its amplitude and shifted in time. So now we might have a difference or a change in scaling of the original sinusoid and its phase, magnitude and phase. Whoa, Bode plots. Now we're talking about something that we've dealt with in another class that I'm teaching this semester, is Bode plots. Now we're connecting linear algebra to Bode plots. Where did that come from? Well, we'll see that it's now inside what we're talking about relative to eigenfunctions. Somehow these Bode plots can be thought thought of as a spectrum content or eigenvalues associated with these signals. So that's where we're trying to move. As I've said already today, is that this finite dimensional stuff, that's what you're going to be held responsible for the final. How does that now allow us to more easily jump into an infinite dimensional space situation when we're dealing with functions? Vectors are not functions, but can we think of them similarly? Here's a quick introduction to this idea. Consider a list. These lists always get me in trouble. But now we have an x1, x2, x3, x sub n, and let's just play with n for now, and suppose that little n is 8. Maybe I need to slide that up a little bit. Did I label my horizontal axis? I now have 8 points. That could represent a vector. In the first component of x, I now could say that, oh, that's equal to 1. My second component is 2, etc. And so now my components in the vector x could in fact represent this signal where I could be time. And as you get further down in that vector, that's now an 8 vector, that represents a later time value of the waveform or signal. What if our list now doubled in size? Or think of that now as slicing this time axis up in half. So 1 now becomes 2, so I now have 2 integers where I did have just 1. And now you can see maybe I'm preserving the general shape of x as a function of I, but I now have twice as many components in that vector x. What if I went to the extreme and said, well, what if we just keep slicing and dicing? That's probably on some infomercial. Maybe not in this form, but you might see an infomercial on slicing and dicing. Now when you see that, you might think of a signal. Somebody's going to look at you like you're crazy, but at least you're always keeping them off guard. Oh, that reminds me of my 501B class. What? They're cooking. Well, I still see vectors. Now if n goes to infinity, what happens? Now you have this I going to time. And x sub I now goes to this continuous waveform. Instead of having this really, really tall vector x, now we've collected it into this smooth or continuous signal. But you could still think of it similar to how if you sliced and diced this fine enough, wow, little n is going to infinity. And each of these components of x is some location on that signal. Just like we had, if I said, what's component 15 in x? Well, you could now find what that is. Or what's component 7 in x, in the first version of x sub I. Now you could say, well, what's x right there? And you could find what that value of x is. So now we're looking at an infinite dimensional vector space, or could be called a function space or a signal space. And we are now interested in what? Performing our addition and scalar multiplication with these functions. Instead of vectors, now we'll think of them as what they are, which are functions, and we can talk about adding functions, we can talk about scaling functions. Let's now dive into this with our understanding of the finite dimensional material with a motivational example. So let's see how our results that we've looked at in the finite dimensional case apply to this infinite dimensional case through a motivational example. Now I'm slowing down. So now let's look at linear operators and what we've looked at before, eigenvectors. And let's look at vector representations in terms of eigenvectors. Remember how if I give you an operator, you could find that operator's eigenvectors. And suppose now that those eigenvectors are capable of forming a basis in that vector space. Now I give you any vector in that vector space and you can decompose it in terms of those eigenvectors. That's what we want to think about now in infinite dimensional case. To get us started then, let's think about, here's sort of a review for the final. Recall the eigenvalue eigenvector equation. If I said, give me the eigenvalue eigenvector equation, what would you immediately see or write down? You'd go turn the TV on, right? TV is equal to lambda v, or TV sub I is equal to lambda sub I v sub I, where v sub I is a particular vector, eigenvector, and lambda sub I is the scalar in that direction of the eigenvector. Or in that linear operator, if you apply that linear operator in a particular direction, a direction determined by the eigenvectors, then you're simply going to, through that operator, move in that same direction or stay in that same direction, just scaled by this scalar lambda sub I. What if we look at that now from a functional perspective? Now consider what this would look like for eigenfunctions. What if we now have a linear operator t, and it's now applied to an eigenfunction? T is our linear operator, and u sub I, let's say, is our ith eigenfunction. U sub I is some function. And if that is consistent with TV is equal to lambda v, what's that going to look like here? If we now have a linear operator and we apply that operator to an eigenfunction, whatever that eigenfunction is, what's going to be the result? Now we're just going to see a scaled version of that ith eigenfunction, where that scaling is some scalar. So now we're going to end up with lambda sub I u sub I of t. Again, this is a function of time, or t, where lambda sub I is the ith eigenvalue, and that is this scalar. So now this is relative to these eigenfunctions. These are now functions of time. You apply those, or you push those through an operator, and now apparently you just get a scaled version of that function out or back. So now let's do that relative to something that I think you're all hold very dear to your heart, which is convolution. So now let's consider, now you are running, lock the doors please. Don't want anybody to escape if we start talking about convolution. Consider an operator you're already familiar with. And that is linear time-invariant convolution. Or maybe I should say, suppose we now have a linear time-invariant system, and we want to figure out how does that linear time-invariant system behave when it's excited by sinusoids or by functions. So now we're going to do that. If it's linear time-invariant, we now know that convolution is going to hold, and y of t can be written as this convolution integral, where y of t is the output function. The input is going to be x, and let's say that that's the signal that we flip and slide. That's how I like to think about signals that are convolved with other signals. And it's going to be applied to a system, a linear time-invariant system, that has this impulse response h of tau. In general, then, we integrate over all time relative to this variable of integration, and now you could say, oh, that's equivalent to saying you have some linear operator operating on a function x of t. T is a linear operator, and it's actually taking x of t into y of t. So you could view this convolution operation as a box. You put in that box an x, and out from that box comes some y, right? Because that box is some linear system, and it likes to shake. It shakes relative to what you hit it with, or what you apply to it. You guys have to remember this lecture. Now you'll never forget it, right? So now you have a lot of shaking going on, but you have this convolution operation. And the block diagram associated with that, if you want to now connect that to earlier courses, you could say, well, I have some system that has an impulse response h of t, and if I apply a function to that input, the output is going to be y of t. Where h of t, you could think of, I like to think of it as a system. You could think of it as a channel. If it was a communication channel, you could think of it as a filter. It's something that processes a signal, and it's a special something. It's a linear time invariant system that when hit with x produces a y. And in this case then, the way that we're thinking of this is t we are going to call it an operator. Why can we do that? When do we classify this linear map as an operator? In general, in our finite dimensional case, what did we call, or when did we start talking about linear maps as operators? Or what did we require of them if we said, oh, this is now a special kind of linear map, it's an operator? What were the properties of an operator that made it different or more special than just a linear map? The domain and codomain were the same. So we started somewhere, we apply this operator, and we come back into that same somewhere space. So t is an operator in this case. Why? Because now if x is a sinusoid, and we have a linear time invariant system, h of tau, we now know that y of t is going to be a sinusoid of the same frequency. So now we have t as an operator because both x of t and y of t are in the same space. So now we have t classified as an operator. If it's an operator, can we actually find an eigenvalue eigenvector, in our case an eigenvalue eigenfunction relationship based on these linear time invariant systems? And our claim in this motivational example, we will claim that e to the I omega t is an eigenfunction of this linear operator t. And is everyone comfortable with e to the I omega t? What is that? There's a whole lot of shaking going on in that e to the I omega t, right? That's just a rotating sinusoid is one way of thinking of it. And you could think of, oh, just projecting that onto the real axis and getting a real sinusoid. And you could say, oh, the projection on the imaginary axis is the complex part. You could think of Euler's relationship of e to the I omega t equaling cosine omega t plus j sine omega t. You now have sinusoids of frequency omega, and you have them in sort of orthogonal directions. And now we're going to say, excite my linear time invariant system with those signals, or with that e to the I omega t. And our claim is if we do that, then we are going to actually see some kind of eigenvalue eigenfunction relationship via this convolution operation. So now let's check this claim. Suppose we now let x be these rotating phasors or rotating signals. E to the I omega t. So when I see that, I just think sines and cosines. And now we're exciting our linear time invariant system with that set or collection of sines and cosines. What's y of t going to do? Y of t now is the result or the output of this convolution operation. Or we can now say that's this integral from tau equal minus infinity to infinity of a flipped and slid signal. That's what I'm going to do to x. So now if I flip and slide that, I take e to the I omega, and my variable is tau. I now flip it by saying minus tau, and I use t to slide these sinusoids wherever I want, depending on what I'm looking for y at that particular time instant. So you say you want y at time 6. I plug in t equal to 6, and I perform this integration. But now I have x of t minus tau. In the convolution operation, that now needs to be scaled by the impulse response h of tau. And now I'm integrating over all tau. And that will produce y of t. We okay with that? This is now just the definition of the convolution integral applied to a particular signal x. And what I'm going to do now is simply say, oh, I'm going to rewrite that or think of that as I'm used to the prefix of this class, ECE, so I might slip and take that I into a j. But I is now the square root of minus 1. So now I'm just rewriting e to the I omega t minus tau in this product form, and the first set of rotating phasors, this e to the I omega t, is independent of the variable of integration. And it's a scalar, so I can slide it out. So now I can slide that e to the I omega t outside the integral, and I'm left with the following. I can now rewrite this convolution integral as this integral from tau equal minus infinity to infinity of e to the I minus I omega tau h of tau d tau. And then what's outside is e to the I omega t. And that's now my y of t. But what did we call this? That was x of t, wasn't it? That's what we let x equal. That's our eigenfunction. We're trying to now find some functions such that when we inject them into this system, we get that same function back, just scaled some way by some scalar. And the scaling is now in this square bracket. You give me an omega, and I can now find what y of t is going to look like for that omega in this integration. So that now this is a scalar function of omega. And omega is given when I give you the eigenfunction x of t. X of t was e to the I omega t. So you were fixing some omega. You were saying, let me apply 6 radians per second as my omega to this system. And now you can plug that same omega value in here and evaluate that integral. But look at that square box, and what do you maybe see? If you now looked at this through your lens that you've now acquired in this class so far, what's another way of thinking of that integral? That's maybe a very vague question, but what if I said, oh, I could write that as h of t e to the I omega t. And now I'm using those triangular brackets as we've used them all along this semester. You could think of this as an inner product, with the first slot of the impulse response, second slot being the signal x of t, and you now what? Take the conjugate of that and then throw it into this particular bracketed expression, and you now have an inner product. So you could think of this like an inner product, that square box or square brackets. So now we have this scalar function of omega scaling our x of t that we excited the linear time invariant system with. Or we can now say, so t of e to the I omega t, that's the convolution integral. We apply e to the I omega t to that, and what happens? We get a lambda of omega e to the I omega t, where this is our lambda of omega. Or we could now make that more definitive, and we could say, and what is this scalar lambda of omega? Well, if we just look at the two expressions and we say t of e of, or t, this operator applied to this eigenfunction, is the convolution integral, then we can identify what lambda of omega is. It's what's in that square box or square brackets. So now lambda of omega is this integral from tau equal minus infinity to infinity of e to the minus I omega tau h of tau d tau. Does that look like anything you've seen in your educational or academic experience? If I give you an impulse response and you push it through this mess of an operation, what are you now generating? Have you seen it called capital H of omega? So now what's another way of looking at this expression? This t, this operator applied to an eigenfunction, is now lambda of omega, this scalar function omega, times the eigenfunction. We could also write that as t of e to the I omega t is now equal to h of omega e to the I omega t. And does that make sense? Our input to this linear system, linear time invariant system, is e to the I omega t. Let's just think of that projected onto the real line so that we're looking at real signals. Now we have cosine omega t. You now hit that system with cosine omega t. You pick an omega and you shake that system at that omega. And that system is linear time invariant. What happens? You can now create this in the lab. You can go up into the stockroom and find some resistors and capacitors and inductors and build this on a circuit board and say, I have a linear time invariant system. And then you shake it. How do you shake it? Well, you get your function generator on the bench and you set it for a particular frequency. You excite that system and you measure the output, and what's going to happen? How are the input and output signals related? I put in a cosine of some omega into a linear time invariant system, this RLC circuit, and what happens? What do you measure? What's the output on your oscilloscope? You can now plot them both. You can plot the input function, x of t, that's some cosine. What's y of t going to look like in the steady state, in the sinusoidal steady state? It's the same frequency of sinusoid. It may just be scaled, bigger or smaller, and it might be shifted. In the steady state, you're going to see two sinusoids of the same frequency, and the way that they will be related is in amplitude. So h of omega is a complex number, and you can find its magnitude and angle to give you magnitude and phase information connecting this input cosine to the output cosine. That's what h of omega is giving us. It's a complex number, but that gives us, you could plot h of omega as a function of omega, and that's our Bode plot. Now we have the magnitude and phase. You give me a frequency omega, I just run to that Bode plot and find that omega and say, here's how your magnitude is going to change and here's how your phase is going to change. And that is h of omega. And what have we done? Now we have an eigenfunction, eigenvector, an eigenfunction, eigenvalue relationship for a linear time invariant system, and now we're dealing with functions. Where now we have our eigenspectrum or eigenvalue being a function of omega. I have to give you an omega and you can tell me what that scalar looks like. So remember, moving into the continuous case, now our vector is e to the I omega t. You give me an omega and you can now think of these sines and cosines. Moving to the continuous case caused indices, these i's, in our earlier thinking of these waveforms, to become continuous as well. Now these eigenfunctions are actually indexed by a continuous parameter omega, which is the frequency. And in our block diagram, we can now think of this as our linear time invariant system. Here is our input, e to the I omega t. This is u of, it's parameterized by omega. You give me a frequency and I can give you what this e to the I omega t looks like. And what comes out? A scaled version of that same eigenfunction. H of omega e to the I omega t. Or you could think of it as a lambda of omega u of omega t. And if that's the case, how many eigenfunctions do we have? How many I to the omega e to the I omega t's are there? How many different omegas can you come up with? An infinite number, can't you? So now we are dealing with an infinite number of eigenfunctions when we're dealing with these infinite dimensional operations, this convolution operator in these linear time-invariant systems. So now we can interpret what we've typically called the transfer function in other courses, which is this capital H of omega, as the eigenvalue spectrum of this linear operator T. So now that we have this eigenvalue spectrum and these eigenfunctions, how did we use eigenvectors in a generic vector space for a given operator? Now recall the importance of an eigenvector decomposition for analyzing operators on finite dimensional vector spaces. If I gave you a generic vector v in a finite dimensional setting, how would you rewrite, or how could you rewrite v if you now have a set of basis vectors that are in fact made up of the eigenvectors associated with an operator? That's just this linear combination of eigenvectors that depend on v. Or we could now write this as a sum of a sub I, e sub I. And this is the way that we could now rewrite or express v, this arbitrary vector, is now written in terms of this set of basis vectors, which are our eigenvectors, written in terms of the eigenvector basis. And if we push that through this linear operator, TV now becomes this summation. Well, let me back that out a little bit. T now applied to this summation of a sub I, e sub I. And what does that now look like? What are the a sub i's? Those are scalars, right? So now, in this particular case, now we're in the finite dimensional case with a linear operator t as some finite dimensional operation in a finite dimensional vector space. I now have this sum of, or a linear combination of eigenvectors. What happens when I hit t with an eigenvector? Now it just gets a scaled version of that eigenvector. Or I could now push that t through these a sub i's, and I could now say, oh, that's the sum of a sub I, lambda sub I, e sub I. Is it not? And now that's easier to think about. Now I just have two scalars that combine to weight each of these eigenvectors without having to worry about this linear operator. And that's now, remember, this TV is a very simple process. And that results from using what? This eigenvector as a basis. So this very simple process results from using a basis that's made up of eigenvectors of that linear operator t. Do you remember how we obtained the a sub i's? So this is a review lecture now. How did we find the a sub i's if they now can be used to combine these e sub i's into forming an arbitrary vector v? How did we find the a's? We just did an inner product, didn't we? We tried to find how does this v align with this vector, or what's the projection, or what's the component of v in this direction of this eigenvector e sub I. That's how we found the a sub i's. And how did we get the a sub i's in v? You've now just told me that that was via an inner product, or another way of thinking of that is as a projection. So that now the a sub i's were just v inner product with e sub I. And that was the component of v in the direction of e sub I, in the direction of that eigenvector. What happens now if we apply this to the continuous case or the infinite dimensional case? Again, we're trying to extend from what we know, what our foundation gives us, into the infinite dimensional setting. What happens in the continuous case? So now, assuming our input, x of t, is made up of a linear combination of eigenfunctions. What does that mean? Well, now let's just call it a sub w. W now is a continuous variable. When we let I get, or when we let n go to infinity, now we move from subscripts or indices I into a continuous variable. So now a of w, let's say, is an inner product of x of t with what? An eigenfunction, which let's call that eigenfunction u of w. Or what we're saying then is x of t, we want to find its projection or its alignment, x. How is it aligned with this eigenfunction e to the I omega t? Amount of x of t aligned with u of omega, which is really just this I of omega t. So you give me an omega, 6 radians per second. Now I want to know how does x of t, this input signal, align to that particular sinusoid? So now we can use this inner product idea where now we have u of t and let's say z of t, and we're now saying that the inner product is going to be z star of t u of t dt. That's our inner product in this infinite dimensional case. If that's the case, we now know what a of w is. A of w is this integral from t equal minus infinity to infinity of x of t. Now I've switched my orientation, but with first slot and second slot, but we now conjugate the second slot eigenfunction, and now we have a of omega, or a sub omega, looking like this. And what is this? A of omega is the component, or the amount, of our input signal x of t aligned with this sinusoid e to the I omega t. So you give me a frequency, 6, and now does x align with that? If it does very strongly, then a of omega is going to be big. If it doesn't very strongly align with that particular sinusoid, then a of w you would expect to be small. And if x was a pure sinusoid of 6, then you can see what a of omega is going to be for different values of omega. We can also look at the other way. Also, x of t can be written as weighted sums of complex exponentials, or sinusoids. That's what these complex exponentials are. E to the I omega t. What am I saying? Well, once you have these weights, you can now express x of t in terms of those weights. Just like once you had the a's in our decomposition of v, now you can write v in using these weights, a sub i's, with the eigenvectors. Now if we have these aw's, now we can write x in terms of those. So that now we could write x of t as this integral from omega equaling minus infinity to infinity of a of omega e to the I omega t. Those are our eigenfunctions, d omega. And we have an integral instead of a sum because a of omega is continuous with respect to omega. So this is an integral because now we're playing with this continuous set of eigenfunctions, and this a of omega is a complex scalar function of omega, and all we're doing really is relating this or connecting this with what we've done before, where v of t was just this sum of a sub I, e sub I, from I equal 1 to n in the finite dimensional case, where now the a sub i's are now a sub w's, or a sub omegas, where that's now a continuous. Omega takes on, remember we sliced and diced it really, really fine, so omega can be anything. It's infinite in size. Here's the finite dimensional case. So now we could say, oh, capital X of omega is a of omega. Here's how we find these weightings in frequency. That's this integral. We say how much of x aligns with these eigenfunctions that's a of omega, where we're now integrating over time. We say, how does x of t align with these complex exponentials, or these sinusoids? That will give us our Bode plot information, x as a function of omega, magnitude and phase. Or we could also look at, so this is now, we can think of these coefficients of little x of t as being in the frequency basis. So now these a of omegas are these weightings or coefficients in the frequency basis. These are functions of omega. This is now the weighting, or the component or amount of x of t relative to each of these sinusoidal frequencies, omega. And we can also think of, so there's the weightings. If I said analyze x of t, you give me an x of t, I can now take it into the lab and tell you how much of that belongs to omega equal to 1, how much belongs to omega equal 2, or how much those different frequencies are components in x of t. Now the other way of thinking of that is in the time domain. X of t could be thought of, now write that in terms of these weightings a. So x of t could be thought of as coefficients of x in the t basis. By that I mean that now we can say x of t is this integral over all of these omegas. We're summing over all the omegas of capital X of omega. That was the weightings, a of omega, that scale these sinusoids. And now what are we doing? Now we are actually integrating over w. So now we really have two different sets of bases. We have x of t. You give me capital X of omega, these weightings, and I can generate x of t. I can do that by saying, now think back of our original example. You could say, oh, x at time 1, x at time 2, x at time 3, and you could find each of those points as the output of this integral. You fix a t, and now you can say, oh, here's the frequency content of your system, signal. This is now what it equals at time I equal 1, at time I equal 2. And you would now slice and dice t to have as many i's as you want. Where is all of this leading? To another just fabulous result. So what can we say? Now we can say y of t is this convolution integral x of t minus tau h of tau d tau from tau equal minus infinity to infinity. That's equivalent to doing the following. We could now integrate over frequency omega equal minus infinity to infinity of the coefficients of the frequency weightings on x times the frequency weightings of our linear time invariance frequency response, the Bode plot of our system, h of omega, e to the I omega t d omega. And why did I say this is such a classic result? Here we have convolution in time. And what's this? This we could actually say is the frequency weighting or the frequency content of y of t in terms of our eigenfunction basis e to the I omega t. So that now if you give me x of t's frequency information, frequency content, capital X of omega, you give me the system and I find its frequency spectrum, h of omega. Now I can multiply those in the frequency domain to generate the frequency spectrum of the output signal. This is just capital Y of omega, and that is, you could think of y of omega coming to you by multiplication in the frequency domain, in omega. So now convolution in time corresponds to multiplication in omega, or multiplication in frequency. And you've heard this throughout your educational experience. Convolution in time is consistent with multiplication in frequency. And why do we go back and forth between time and frequency? Sometimes it's easier to work in the frequency domain. We've converted all this differential equation stuff into algebra in the frequency domain. Let's now verify that. So let's derive that. Let's show, based on our understanding of this frequency content of these different pieces of x, of h, etc., let's derive that. So now we have y of t is equal to this convolution integral from tau going from minus infinity to infinity of x of t minus tau h of tau d tau. But now I want to rewrite h of tau in terms of its frequency content. I can now do that because I can find its coefficients, its weightings in the frequency space. So that now I can say, oh, that's the same as this integral from tau equal minus infinity to infinity of x of t minus tau. And now let me replace h of tau with this integral from omega equal minus infinity to infinity of h of omega e to the I omega, let me say tau, since it was h of tau, with respect to omega d tau. Just rewriting this h of tau in terms of its eigenfunction decomposition. What's the frequency content of h of t? Well, it's expressed as h of omega. Now let me start moving integration operations around. Meaning, let me take that integration with respect to omega and sliding it all the way to the left. So now I'm integrating h of omega from minus infinity to infinity. I'm integrating with respect to tau from minus infinity to infinity, and I have x of t minus tau. I have h of omega. I have e to the I omega tau d tau d omega. Haven't done anything really. Just put everything underneath both integrations. Slid x of t minus tau inside the integral with respect to omega, which is fine. Now what do I want to do? Now here's maybe the most challenging part. I'm just going to do a change of variables. So let me clean this up by saying, well, if I would let sigma be t minus tau, x of t minus tau would be simpler. And I can do this for a fixed t. And if I do that, what if I solve it for tau? What does tau now equal? That's just t minus sigma. So anywhere I see a tau, I can replace it with t minus sigma. And if t is fixed, little t is fixed, what's the change in sigma? What's d sigma? T is fixed. That's now minus d tau. So wherever I have a d tau, I can replace it with minus d sigma, and I can do this change of variable. Meaning, let me now rewrite that. I apologize that my screen's not big enough, but now I'm not changing the first integration, but now I'm changing the second one, and I'm replacing, tau with sigma. So now, if sigma is replacing tau, and I'm going from minus infinity, sigma is going from plus infinity on the lower limit. And the upper limit will be minus infinity. So now sigma is going from infinity to minus infinity. I now have x of sigma, h of omega, e to the I omega, t minus sigma, minus d sigma dw. And that minus I'm going to use to reverse the limits on my integral with respect to sigma, so that my lower one becomes minus and my upper one becomes plus. And I can now say I have the following. Y of t is now this integral from omega equal minus infinity to infinity of this integral from sigma going from minus infinity to infinity. And what I want to now put in here is x of sigma e to the minus I omega sigma d sigma. And outside that, I have h of omega e to the I omega t d omega. And what is this blocked expression? That's my frequency content of x, of t. This is now the weighting in frequency of x of t. I'm now just saying, what's the projection of x in the direction of these eigenfunctions? That's now this capital x of omega. These are the weights of x of t, the frequency content of x, and now I can rewrite y of t as this integral from omega equal minus infinity to infinity of x of omega, h of omega, e to the I omega t d omega, where this is really just a function of omega, and I could call that capital Y of omega. This is now the eigenvalue spectrum of Y of t. What's the frequency content of Y? So all of this now, all of Fourier analysis can be thought of similar to eigenvalue eigenvector or eigenvalue eigenfunction analysis that you've spent all semester playing with. Now you can think of these this Fourier material in terms of linear algebra, and that's why linear algebra is done right. We'll pick up somewhere close to here by talking about sets of functions so that we can now think about sets, how can we partition those, and then how can we find distances for those vectors or those functions in this infinite dimensional case. We'll pick up at that point the next time. And I may add in a little bit more, but essentially all of Fourier analysis now you can think of the way that we've been dealing with eigenvectors in finite dimensional cases.